All right, good day. Uh, last time, right? Last video, we finished our introduction on matrix multiplication, right? And now we will finish the rest of this thing so we can finally get to actually applying matrices in real life, right? In real life, or in problem solving, right? So that is completely different parang section of this topic. But for now, let's just get to finishing the determinant as well as its other things, right? Its other ang tawag dito? Is its other parts, right? The minor and the cofactor. Okay? So, right, the determinant is basically something that it kind of is the identity of the matrix that you're working with, right? But the determinant is only possible for square matrices, right? So that means that if you want to take the determinant of this matrix X or this matrix Y, hindi siya pwede, right? You will not be able to get the determinants for these things, right? And so, right, we usually have general formulas for 2 by 2 and 3 by 3 matrices, right? So say for example, in here we have our sample matrix. Let's just call it letter S for sample, right? Let's call it sample S. And we have here a 2 by 2 matrix A, B, C, and D. As we can see here, this is a 2 by 2 matrix, right? 2 rows, 2 columns, right? And the determinant of S, what you can do is just put det of S, or what you can also do is S, and then you put absolute values, right? In this case, what a determinant is basically a kind of a code that that transcribes, right, information from a matrix, right? I won't go too much into detail because that has to do with linear transformations, that kind of thing. But basically, if you want to think about these things, right? If you want to think about the determinant as an actual number, for a 2 by 2 matrix, say for example, we have here 3, 2, and then 5, I don't know, 1, right? What you're going to do is you're going to plot these things, right? What are we going to plot? We're going to plot 3, 2, and 5, 1, right? 3, 2, and 5, 1, right? Okay, let's just have this, and then something like this. Okay, so 3, 2 is 1, 2, 3, 1, 2. So this is 3, 2. Let's try and draw a vector. Oops, a vector. There you go. That is your 3, 2. And then your 5, 1, 1, 2, 3, 4, 5, 5, 1. So that thing is your 5, 1. What this creates basically is a parallelogram, right? This creates a parallelogram. You might be wondering, where's the parallelogram? It is created by this as well as as well as this. And so now the determinant for this thing is this area, right? Is this area. And because, right, this 5, 1 is on the bottom of this 3, 2, it's negative. And so it's a very complicated kind of thing. But if we were to get the determinant for this, let's just get the formula. It's going to be AD minus BC, right? AD and then BC. So in this case, the determinant for this, say for example, let's have this as a letter P, right? Matrix P. The determinant of P in here will be equal to 3 times 1 is 3 minus 2 times 5, that is 10. So this will be negative 7. That means this total area right here is negative 7, right? If, for example, we've now switched these things, instead we have 5, 1 and then 3, 2, this will now be, right? This will now be positive, right? This will now be positive. So we will have here 10 minus 3, that is 7, right? Okay, so either which way, the magnitude of this is going to be 7, right? And if you're thinking already, okay, what about 3D? It will be the volume of the parallelepiped, right? That is created by the 3 vectors that you're going to see, right? But enough of that, right? What we just want in here is for me to teach you how to be able to compute determinants, and not only determinants for 2 by 2 and 3 by 3, but theoretically for higher matrices. And if you're wondering, what about the determinant of a 1 by 1? Well, it's just the number, right? It's just the number, okay? And so now, let's have a generalization, or not a generalization yet, but what about the formula for the 3 by 3 matrix? Say, for example, here you have a matrix T, which is now a 3 by 3. Let's say, for example, I don't know, A, B, C, right? And then D, E, F, and then G, H, I. G, H, I. Okay? The determinant of T is going to be a bit more involved, right? Involved in the sense that this will be, let me see if I'm getting this correctly, AEI plus BFG plus CDH minus, right? Minus GEC minus BDI, BDI minus AFH. There you go. Or let's just put this as CEG. So that is the determinant T. So you might be saying, how am I able to recite this like off the top of my head? I'm actually seeing in here, right, for the 2 by 2 and 3 by 3 matrices, I'm doing what we call the basket weaving rule, or Sarris's rule. You can look this up if you guys would like, right? Sarris's rule, SARRUS, Sarris's rule. But basically, I'm creating in here a basket weaving technique. What do you mean? Right? I'm creating in here diagonals. Right? In this case, I'm creating in here a diagonal that is AD and a diagonal here that is C and B. And basically, what is happening is that if your diagonal is going down, you put it with a plus sign. If your diagonal is going up, you put it with a negative sign. That is why this determinant, the determinant for this matrix S, that's why it's going to be A times D, and because it is positive, it's just positive, right? And then B times C, and because there's a negative, because this diagonal is going up, that's why it is AD minus BC. Okay? On the other hand, you might say to yourself, okay, there's only one diagonal in here. It's AEI, which you guys can spot hopefully, and GEC, right? Which you can hopefully spot in here as well. But that is why, right, there's an AEI and there's a CEG. What about these four? Well, what I'm doing in here is that I am creating, right, a kind of a teleportation, right? What do you mean a teleportation? Let's just write this down again. A, B, C, D, E, F, G, H, I. What I'm doing in here is that I am trying to repeat this on the right-hand side. A, B, D, E, G, H. Right? That is what is happening. And now, why did I not write down the C, the F, and the I? It's because this is enough. Right? This is enough. What do we mean this is enough? You will be able to create AEI, BFG, and then CDH. If I were to create another CFI, Eddie, you would replicate the AEI in here. So that is why that is not needed. We only need we only need to repeat the first two rows of this, right? On the other hand, you will see in here a GEC, an AFH, and a BDI. And all of these are going up, so they're all negative, right? There you go. And all of them are going down, so, all of them are going down in here, so they are now positive as well. AEI, BFG, and CDH. Essentially, I can do this because I can see kind of a teleportation thing. Say, for example, if I write down this diagonal, it can teleport to the other side here. So that is a positive, right? And this one, you know what? Let's color code it with orange. This thing will teleport to the other side, right? That is your positive, and another one in here, your C, will teleport to the other side, and then it will complete the D and the H. The same thing goes for your F and H in here. If you're going to put this diagonal up, it will teleport to the A, negative, and then, right, either the B and the D in here, if you put the teleportation, it will go up to here, right? So your I, if you put it up, it will go to the B and the D. So as you can see here, very complicated look, right? But if we're going to separate all of them, right? If we're going to separate all of them, you will see in here all of the positives and all of the negatives. A, B, C, D, E, F, G, H, I. Here you go. This is for the positive version. I will copy and paste this for the negatives. Yan. So you will see in here the main diagonal A, E, I. So this is like we are just doing a little word search, right? A, E, I. And then this B, F, G. And so you will see in here a little teleportation happening. And then, excuse me, for C, D, H, that is also your teleportation, right? So all of them are going down. So that means they're all positive, right? And for this one naman, right? For CEG, it's going up. And then for BDH, right? Sorry, BDI pala. That's going up as well. Sorry, let's just do this here like this. And then the AFH works as well like this. Okay? So all of these are positive and all of these are negative. Now you might say to yourself, okay, all right, I'm ready to tackle the fourth one, right? The 4x4. So say for example, we have here a matrix U, right? A matrix U, and let's just say to ourselves, right? I don't know, the first 16 letters of the alphabet, kaya A, B, C, D, E, F, G, H, I, J, K, L, right? M, N, O, P. Now, you might say, oh, I know how to do this. Number 1 is here, right? Number 2 is here, right? Here. Oops, my goodness. Here. Number 3 is here. And then number 4 is here. No, right? That's not how it works. It just so happens that it works for the 2x2 and the 3x3 cases. And so now, here is how we're going to generalize your determinant. That is going to be, right? All right, okay, I'm gonna have to warm up in here, right? What we're going to do in here is for us to get the determinant U, you're gonna have to find these things, right? Say, for example, you take a row, right? Let's take a row A, B, C, and D. Let's take that row right there. And let's say, for example, we will have to go through A, B, C, and D. Let's start with A, right? A is at the first row and first column. We will now remove all of that, right? And we will be left with this little tiny, with this tiny little, what do you call this? Tiny little mini matrix. And what you're going to do with this matrix is you're going to get the determinant of this matrix. Okay, no big deal. So basically, what you will get is this, right? A times the determinant of, right, of FGH, JKL, and then NOP. Okay, no big deal. And then we move on with the rest of the row. B in here is at the first row, second column. You will now remove everything there and you will be left with EIM, GKO, HLP. If you stick them all together into one mini matrix, you will now, right, do the same thing. B, and then the determinant, right, the determinant of, right, the determinant of EGH, right, IKL, and then MOP. So basically, you have done this, right? This is your matrix right here because you removed everything that is touching, right? That is the coordinate of your B. Now, why am I not putting here a sign? It's because this was positive. Now, this is negative. And so this pattern continues. You now have plus C, and then the determinant of, right? Pause for a little bit, see what the resulting matrix should be, right? See what the resulting matrix should be, and what should be the correct one is E, F, H, I, J, L, and then M, N, P, right? And then minus D, determinant of, right? E, F, G, I, J, K, and then M, N, O. This is the determinant of your 4 by 4 matrix. And I know that sounds horrible, right? And if you do the math, right? If you do the math, this will factor out to be, this is, each determinant in here has 6 terms, right? And there are 4 terms in here in total, so there will be 24 different terms. In here there were 6. In here there were 2. So, as you can kind of guess, if you have a 2 by 2 matrix, you will require 2 factorial terms. If you have a 3 by 3 matrix, you will require 3 factorial terms. If you have a 4 by 4 matrix, you will require 4 factorial terms. And we can go on and on, right? For the 5 by 5 matrix, right? Suffice to say, that is a lot of work, right? That is a lot of work. And tingnan natin, right? See if this generalization works for the 2 by 2 and the 3 by 3, right? So say, for example, we have this S right here, right? A, B, C, D. When you want to get the determinant of S, what you just have to do is, right, take this, cancel everything, and then you have D. Oh, so it is A times D. And then we continue the what do you call this? The pattern, right? B. Cancel, cancel, you will now have C. Oh, so it is AD times BC. Okay. I am obscuring from you guys a little detail. That little detail is, right, is our minor and our cofactor, right? So the minor in this case and the cofactor are kind of the same thing. The minor in this case is going to be the resulting determinant in here. This thing. This thing is what we call a minor, right? Minor, hopefully it kind of makes sense for you guys that it is kind of like a smaller version of the matrix, right? And then the cofactor is going to be the minor, and then if you add the sign, that is going to be your cofactor, right? That is going to be your cofactor, right? Here's the deal. The cofactor is not just a simple plus minus plus minus. There's actually a computation that goes into it. Say, for example, what if instead of choosing this row A, B, C, D, what if we chose E, F, G, H? Instead of this, right? Instead of this, right? We would get a different computation, right? Say, for example, we want to get the determinant of U through another row, right? So what we will do is, right, we pick E and then we cancel everything out. We will get, right, the determinant of BCD, right? BCD, JKL, and then NOP. And you might expect that, oh, this is just E, but it's not. It's negative. And now, for some reason, the pattern is negative, positive, negative, positive. So what gives, right? What makes this thing positive, negative, positive, negative, and this thing negative, positive, negative, positive? There is actually, right, a rhyme and reason to all of this, right? The rhyme and reason is that the general formula talaga to get the determinant of this thing, right, of any kind of function, or sorry, of any kind of matrix is once you select a row, right? Once you select a row, what you usually, how you usually index, right, an element is by this, right? We have here our matrix name. It is letter U. It is usually written as a capital letter that is usually blackboard bold. Elements in U are usually denoted with the small letter and then with the row number and the column number. Usually they are in terms of I and J. In this case, we have I and J in here, so hopefully that does not present some confusion. But say, for example, you select a row. What you will then do is you will cycle through 1, 2, 3, 4, the 1, 2, 3, 4 columns. And so what is happening in here is that you will cycle through your J from I1 to the number of columns, right? Columns. And what will you do? You will now do, right? A, IJ, M pala, M, because we're looking here at an M. M, IJ, this is basically the element that that belongs to your I and the J, right? So say, for example, you pick the second row. You will now have M21, M22, M23, M24 for this row, right? You will look at each and every one of them, and then you will have the minor, right? The pertaining minor, right? The minor that belongs to MIJ. And it does not help that the minor is usually denoted with a big letter M. So I feel like we should have another thing in here. Maybe a letter A. Yeah, letter A. Yeah, and so A, then you will have in here the element AIJ and then the minor at IJ. And so there's something wrong in here because what you need to do is you need to include, right? How am I going to do this? -1 raised to I plus J. That is, right, this is your minor, right? This is your minor. And if you include this computation of -1 plus raised to I plus J, this is your cofactor, right? That is your cofactor. And so now, what do you mean, right? In the beginning, right, when we were doing this, we selected this row, right? And so I'm going to label in here the row and column number for each of the elements of this row. Row 1, column 1, row 1, column 2, row 1, column 3, row 1, column 4. Notice, this is what we were doing earlier. This is the element at row 1, column 1. This is the element, row 1, column 2. This is the element, row 1, column 3. This is the element, row 1, column 4. And the minor in this case is this thing, this thing, this thing, and then this thing. How we were able to decide the sign is through this. Row 1, column 1, 1 plus 1 is 2. Right? And that is an even number. If you raise -1 to an even number, it will result in +1. That is why this thing was positive. And now 1, 2. So 1 plus 2 is 3. That is now an odd number, negative. Even, positive, odd, negative. That is how we were able to create that sign, right? That sign assignment. So in this case, because this is now 2, 1, 2, 2, 2, 3, 2, 4, notice now that the first and the third terms create odd numbers. That is why they are now negative. And so actually, if you want, right, I don't know how you guys would like to solve for this kind of thing. You can already kind of draw a table, right? Plus, minus, negative, positive, and then you can just tile the whole matrix like this. Just so you can just so you can remember siguro, right? The thing is this. You might already be thinking, I don't actually need to compute this because my calculator, most likely, if you guys are using a board-approved calculator like a Casio or a Canon, right? A Canon F789 SGA, that can compute determinants of 4x4 matrices. The Casio FX570 sadly cannot, right? Your ClassWiz can probably, but it is not board approved. So if you want to use something that you will be, right, that you will be using for your board exam, ayun, right? Either the Casio FX570ES or the Canon F789 SGA. In this case, yes, I know you can. However, right? I want to be able to see from you guys that you understand this process of determining the determinant, right? Technically, you can just tell me the number. Okay, sure, whatever, right? But the thing is, how, right? How? Okay. Speaking of how, right? And by the way, we've done the determinant, the minor, and the cofactor already. Let's just try and get the determinants of some things. Excuse me. If you remember this, right? Our values for x and y, matrices x and y in here, sabi natin, these are non-square, so we do not have determinants for x and for y. However, for p and for q, we have determinants for them, right? These things are square, okay? And so let's try out our determinant of p. Right? Let's try a determinant of p. This will be negative 6 times negative 3. That will be positive 18. I don't know what this is going to be. 19 times 24. Let's just use our calculator in here. 18 minus 19 times 24. Negative 438. Negative 438. Okay? Sure. Next. Ito na, determinant of q. This is gonna be a little bit more difficult, right? And maybe we should move away to some other location, right? I'll just copy this. Negative 22, 16, 38. These are some big numbers. Negative 10, 10, and 25, 9, 0, 3. Oh, that's good. Okay. Good. And now, right, if you guys are still a bit unsure about your skills in trying out the 3x3 determinant, you can definitely just copy the first two rows in here. Negative 22, 16, negative 10, 10, and then 9, 0. And then you can draw your, right, your diagonals. 22, 10, 3, 16, 25, 9, 38, 10, 0. That's very good if you have a 0. Right? 9, 10, 38, 0, 25, 22, 3, 10, and then 16. So I cannot see I cannot see my stuff. Okay? So negative 22 times 10 times ano to 3? 3. That is a 3. And then this one 16, 25, and 9. 16, 25, and 9. And then ito, I will no longer write this because this is multiplied by 0. We don't need to do that. 9, 10, 38 in here. So minus 9, 10, 38. And if you're wondering why there's a negative in here, it's because this thing is literally a negative. This one I will also not write because there is a 0. And then we will have here 3, negative 10, and 16. Because there's a negative in here, this will now be positive. 3, 10, and then 16. And so if we put all of this together, let me actually get my calculator. Negative 22 times 10 times 3 plus 16 times 25 times 9 minus 9 times 10 times 38 plus 3 times 10 times 16. The answer is what? It's a 0. Okay, all right. If you say so, right? It's a 0. Oh, okay. Wow. Very interesting. For some reason, this is a 0. I cannot see the 0 yet. Anyway, right? Apparently, that is a 0, which is very cool, right? And so now, that is just a very simple parang exhibition as to how to get determinants in real life, right? And now, we will go to determinant properties before we go to adjoint and inverse. That is our last kind of topic before we go off into the real world for us to start solving. And so for now, I have here a couple of things that I want to show you all, right? Determinant properties. Ito. The first one, the first property that I would like to share. Saan ko ba pwede ilagay? Dito na lang tayo. Properties. The first one I'd like to share in this case is that the determinant of your transposed matrix is still the same as your determinant of the original matrix. So let's just try this out, see if it works, right? Of course, this is not proving, right? But I mean, you know what? Let's try and prove it for a 3x3 case, okay? Let's try it with letter A. And again, we will do, right, A, B, C. And hopefully at this point, you guys have acclimatized a little bit to, right, ano tayo ito? To getting the determinants of things. If that is your A, then your A transpose will be along this line. You will now just look at switching everything over, right? Switching everything over. We will see that our current, right, main diagonal is still untouched, but now A, B, C, D, E, F, G, H, I. Okay, let's get the determinant of A, right? In this case, you look here, right? That's your first diagonal. This thing is your second diagonal, and this thing is your third diagonal. So that will be AEI plus BFG plus CDH. Next, your negative diagonals. This one first, this one second, this one third. Okay, so minus CEG minus BDI minus AFH. Okay, let's try the determinant of A transposed, right? A transposed. Okay, this one AEI, DHC, and BFG. Very interesting. AEI, still the same. DHC, which is just the same thing as CDH. And then GBF, which is the same thing as BFG. So far, so good. Cancel, cancel, cancel. Next, CEG, right? Still the same thing. First one. And then FHA. And then DBI. So, at the very least, for a 3x3, we can prove that the determinant, right? Okay, let me just write this down first. CEG, there's still a BDI, and there's still an AFH. So everything is still the same. Okay, so at the very least, we have proved that for a 3x3 matrix. Okay, next, right? That is our first property. Our second property now is if you have two square matrices, right? And if you multiply them together, right, it will be the same, or their determinant will be the same as if you just multiply the determinants of the matrices themselves. Very interesting, right? And so let's try this out. At the very least, for sabihin na lang natin ay 2x2 so that we don't get muddled in so much parang confusion. A, 1, 2, 3, 5. Okay. And then B, let's have, I don't know, -1, 4, 2, I don't know, -3. Okay, that means that your AB, right? Your AB will just be 1, 2, 3, 5. And then your B is -1, 4, 2, -3. Now, that means, right, if this is a 2x2, right, 2 rows, 2 columns. This is also 2 rows, 2 columns. Because these two are the same, right, this will now be our new size of our matrix row and column, which, surprise, surprise, is still a 2x2 matrix. And so if you remember what's supposed to happen in here, for the first row, first column, first row, first column, we will now do piecewise multiplication. 1 times -1 is -1. 2 times 2 is 4. -1 plus 4 is 3. Next, first row, second column. First row, second column. Right? Oops. First row, second column. 1 times 4 is 4. 2 times -3 is -6. So that means 4 minus 6 is -2. Second row, first column. Second row, first column. 3 times 1, -3. 5 times 2 is 10. -3 plus 10 is 7. And finally, second row, second column. 3 times 4 is 12. 5 times negative 3 is negative 15. So 12 minus 15 is negative 3. Okay. Sige. And now, I challenge you guys, what about BA? Right? What about BA? So, you can do that on your own. How does it factor in to this? Right? Think about it. What will the determinant of BA be equal to? Right? What will that be equal to? And so now, right? Oops. So now, your determinant for A, very easy to get, right? It's just AD minus BC. 5 minus 6. Your determinant of A is negative 1. B, the determinant of B is negative 1 times negative 3. That is going to be positive 3 minus 8. So 3 minus 8, that is negative 5. And that means your determinant of AB, hopefully, that should be positive 5. Let's see if it works. 3 times negative 3 is negative 9. Ako, patay tayo dyan. 7 times 2 is negative 14. But because it is going up, it will be positive 14. And surprise, surprise, negative 9 plus 14 is indeed 5. So that means your 1 and your 2, they are indeed the same. And so if you've given the determinant of BA any thought, even if, right, I know, right, even if we have yet to what do you call this? Even if we have yet to get the value or the matrix BA itself, I know that the determinant of BA is also 5. Right? How do you mean the determinant of BA is also 5? The thing now is that, well, the determinant of BA, if we're being very specific about this, is just the same thing as switching the order. The determinant of B times the determinant of A. And what you notice, this is just a number times a number. A, B. This is just B and A. These are numbers we're talking about. These are not matrices. So that means multiplication is commutative. You can switch the order. And so in this case, even if I don't know the value of, the matrix BA itself, I know that it will have the same determinant as the matrix AB. Okay? Most likely your BA, my guess, right? My guess as to BA is negative 3, negative 7, 2, and 3. I think that's my guess. That's my guess. Okay, I can't resist. Okay, let's just see. Negative 1, 4, and then 2, negative 3. And then we have 1, 2, 3, 5. Hopefully, you guys can follow my vision. This one is this times this. Negative 1 times 1 is negative 1. 4 times 3 is 12. Oh, that is very far. Okay. Oh my. All right, so that means that negative 1 plus 12 is 11. Oh my goodness. Okay, so this is very far. Okay, 11. Okay, 11. And then first row, second column. First row, second column. Negative 1 times 2, negative 2. 4 times 5 is 20. 18. Okay, second row, first column. 2 times 1 is 2. 3 times 3 is negative 9. So 2 minus 9 is negative 7. And then second row, second column. 2 times 2 is 4. Negative 3 times 5 is negative 15. 4 minus 15, negative 11. What is happening? Okay, so let's get the determinant of BA. Okay, this is very interesting. Determinant of BA is 11 times 11, negative 121. And then this one, because it's negative, we'll turn this into a positive. 18 times 7, 35, 105. Is that right? Yeah, 105. Okay, I must have done something wrong. What? Wait. 11. Yeah, 11 times 11. Yeah. 18 times 7. Oh, sorry. 18 times 7? Oh my gosh. Okay, sorry. 18 times 7, 7 times 8 is 56. So it's 126 pala. Okay. I have done something wrong. So that is indeed still 5. Very interesting. Right? Very interesting. The determinant of this very scary looking thing is still 5. Okay. Very cool. All right. There you go. Right? That is property number 2. Okay. Now, what if, right? What if we have something like this? If you interchange, right? If you interchange any two rows or columns, what happens to the determinant, right? What happens? Well, let's just try, right? Let's have another thing, what other things have we yet to use? Letter H. Yeah, letter H. Okay. Let's have here a 3 by 3. A very simple 3 by 3. 1, 0, 4, 2, 2, 7. Nope. No. 3, negative 2, negative 1, and I don't know. 2. Okay. Let's try and get the determinant of H. Okay. And now 1 times 2 times 2, that is just 4. 0 times 3 times negative 2, nothing, right? 4 times 2 times negative 1, that is negative 8. And now we go to the upward diagonals, negative 2, negative 2, negative 2, 2, and 4, that is 16. It's plus 16 because there's a negative here already. 1, 3, and negative 1, that is positive 3. And then 2, 0, and 2, we will not include that because there's already a 0. So if we put all of these together, we will have 16 plus 3, 19 plus 4, 23 minus 8. That is a determinant of 15. Now, watch what happens if we try and interchange, right? So this is H prime now. Let's try and interchange 2 rows, right? Let's try and interchange 2 rows. 2, 2, 3, 1, 0, 4. Then negative 2, negative 1, and 2. Let's try out the determinant of H prime. Okay, let's try this out. 2, 0, 2, nothing. 2, 4, negative 2, that will be negative 16. So very interesting. All right, next. We continue. This one is done. This one is done. This thing is next. 3 times 1 times negative 1 is negative 3. Okay, next. Right? The upward diagonals. This one, nothing. This one is 2 times 4 times negative 1 times negative 1. That is 8. Okay. And then, what do we expect from the last one? This is done. This is done. This is the last bit. Right? 2 times 1 times 2 times negative 1. That will be negative 4. There you go. Right? So now, right, what do we expect the determinant for this will be? It's just everything in here is the negative version. So that means the determinant for this letter H is going to be negative 15. Okay. Okay. Right? Very interesting. And now, say for example, we interchange these two. Right? We interchange these two. What do you think will happen? It will go back actually to 15. So you might say, wait, what? What if I interchange all three? It depends. As you can see in here, or rather, as you might have already kind of guessed from earlier, this matrix is actually parang an endless cycle of repeating repeating values. Say for example in here in Saras's rule, right? We can just look ahead, right? Look to the right and we can see copies of these values, right? What do we mean? In this case, look at this thing. If we interchange these two values now, say for example, we have H double prime, right? We have H double prime. We have now done 2, 2, 3, negative 2, negative 1, 2, and 104. Notice if this is our box, Now, look at the box. This is the bottom of the box, and this is now the top of the box. What we've done here essentially is just we've replaced, or rather we've rearranged the values of our matrix. And notice, I will do something that I consider as like very weird. I will now push all of the values in here to the right. Essentially, what I'm doing now is I will push all of the all of the values one column forward. So now H triple prime, right? If we try and do this, I will now move these, right? I'll now move these here, and I will move this to the other side. We will have 3, 2, 4, and then we will have 2, 2, -2, -1, 1, 0. Essentially, what we have done is now this thing, this weird thing, right? That is now the box. It's now disassembled. Look at this. This is the bottom left corner. This is the bottom right corner. This is the upper left corner, right? Look at this. And now this is just the upper right corner. Everything in here is still essentially the same, but we have just, kumbaga, we've just styled it a different way, right? We have just styled it a different way. What do you think will be the determinant of this thing? If you try this out, the determinant for this H triple prime will be the original. And so you might say to yourself, so what is wrong with this thing? Why is this -15? Because you cannot find a way to make the box fit here. Look at what happened, right? This is the middle. So this is the middle. And then suddenly, you're now looking at the top, and now you're looking at the bottom. Essentially, you have now broken the pattern of the box. If you do not break the pattern of the box, you essentially will still have the same determinant. You can try this out, of course, right? Feel free to disprove the correctness of this thing, right? But yeah, if you conserve the symmetry, or not the symmetry, but the pattern that exists within the matrix, right? It doesn't matter. Right? Essentially, say for example, if we just have these values, right? Let's have these values, these 9 values, copy, and then we paste them somewhere. Paste. We paste them again. Paste. Paste them again. Paste. And we keep tiling the board like this, right? We keep tiling, and oops. We keep tiling it like this. So on, so forth, right? No matter the kind of 3x3 matrix that we box, say for example, something like this will still have a determinant of 15. This will still have a determinant of 15 for all I care, right? This still has the determinant of 15, right? And just to cap things off, something like this still has the determinant of 15. Where's the original matrix? 104 is the one on top. So the green one is the original, but the red, the yellow, and the blue ones still have a determinant of 15. That is the cool thing about this, the properties of this matrix, of just determinants in general. Okay? So all of those boxes have the same determinant. Really cool. Okay. Now, we continue. Right? The next thing, right? The next property that I would like to show to you is what if two rows or two columns are equal? Right? What will happen? Say, for example, let's just have a really short one. Letter J. Right? Letter J. I don't know, 2, 4, 2, 4. From what you can already see in here, that is just gonna be the determinant of this J matrix will just be 2 times 4, 8, minus 2 times 4, 8 is 0, right? If you want a kind of like a visual representation of this, right? If we're going to draw this in the same kind of thing that we've done earlier, right? Let's just say Where do we put this? Maybe here. Here, and then, oops. Here, and then here, right? Your 2, 2, that's going to be the first vector we plot, and then 4, 4 is going to be other vector we plot. So this is your 2, 2, and this is your 4, oops, this is your 4, 4. And so you might say, what is the area of the parallelogram bounding these two things? Nothing, right? Because they are linear. They create a line of their own, right? And so now, based on that, we can kind of generalize what's supposed to happen. Oh, so by the way, this is 4. We can generalize what's supposed to happen. So now, say for example, what if this K is a 2 by 2 matrix, say for example, 1, 3, and then 2, 6. What do we think the determinant will be? It's 0, right? The determinant of K is 0. Why? Because look at this. 1, 3 and 2, 6 will fall on the same line. If you want to, of course, just like try and compute the determinant for yourself, go ahead, right? 1, 6, 3, 2, completely fine. Say for example though, something as large as, I don't know, L. Matrix L is a 4 by 4, right? 2, 4, 6, 8, 1, 2, 3, 4, negative 7, 10, I don't know, 115, 4, I don't know, pi, e, I don't know, pi raised to e raised to pi. Why do I not care about these last 8 values? Is because look at this, 2, 4, 6, 8, and 1, 2, 3, 4. They are the same. Well, they're not the same. More like what you can do is you can kind of factor them out, right? There is a common factor here of 2, and whenever you detect something like that going on, that is going to be, right, a cause for you to just say that the determinant for this matrix is 0, right? You detected that there was a 2, 4, 6, 8. There was a 1, 2, 3, 4. The determinant for this thing is 0. Okay? I mean, I can try it out with the canon right here. Let's try. Matrix A is a 4 by 4 matrix. 2, 4, 6, 8. And then 1, 2, 3, 4. And then negative 7, 10, 115, 4. And then we have pi, e, pi raised to e. I don't know why I did this. Pi raised to e, and then e raised to pi. E raised to pi. Okay, let's try and get the determinant for this thing now. Number 3, determinant. The determinant is 0, right? So I feel like they did the same thing, that they were like, you know what, these two things, they are factorable, therefore it's now 0. And oops, I think I want to I want to jump on this a little bit more, right? I want to jump on this a little bit. Okay, let's have, say for example, a 3 by 3 matrix right here. 3 by 3 matrix. What? I'm always stuck up with the names. Letter N, right? Say for example, very obvious, 1, 2, 3, and then 2, 4, 6, and then I don't know, 3, 0, 5, right? Because of the 1, 2, 3, 2, 4, 6, you can say that, oh, the determinant for this thing is 0, right? The determinant for N is 0. Let's just try and see, right, if that is indeed correct. Okay? 1 times 4 times 5, that is 20. 2 times 6 times 3, that is 36. And then 3 times 2 times 0, there's nothing there. So we switch to the negative, right? Our negative diagonals. 3 times 4 times 3, minus 36. 6 times 0 times 1, nothing. 2 times 2 times 5 is negative 20. So really is going to be 0. Now, the challenge is this. What if you now see 1, 2, 3, 3, 5, 7, 3, 0, 5? What do we think now is the determinant of, I don't know, let's call this n prime. What is now the determinant of n prime? I mean, let's try it out, of course, right? 1 times 5 times 5, 25. 2 times 7 times 3 is 42, right? And then 3 times 3 times 0 is nothing. 3 times 5 times 3, that is minus 45. And then 3 times 2 times 5 is minus 30. Is that it? Yes, cool. And then, is that right? Hold on. 3 times 5 times 3, 0, 7, 0. And then 3 times 5. Yeah, okay. So now, the thing about this is that this is going to be, whoa. This is gonna be equal to 25, 42, 67. This is gonna be minus 75. This is negative 8. Okay, so what's the difference? Of course, this is not the same, but there may be a faster way going through all of this. If we remember that this is 2, 4, 6, and then this is now 3, 5, 7, what if, right, we were to look now into another matrix? And the other matrix in here that I would like to show you guys is 1, 2, 3, 1, 1, 1, 3, 0, 5. Let's just try it, right? 1, 1, 5, 5. 2, 1, 3, 6. 3, 1, 0, nothing, right? 3, 1, 3, 9. 2, 1, 5, minus 10. And then 1, 1, 0, nothing, right? So 5 plus 6, 11, minus 19, negative 8. And so you might now say to yourself, okay, so what's the relationship? I know that these two are the same, and that cannot be by coincidence. Yes, it is not by coincidence. What gives, right? What gives in this situation is that, look, we just added basically in here, right? The 1, 1, 1 in here, we just added twice our row 1. This is our row 1, right? If what we have done is we have done R2 plus twice our row 2 plus 2 times our row 1, we arrive at the same thing. 1 plus 2 times 1 is, well, 3. 1 plus 2 times 2 is 5. 1 plus 3 times 2 is 7. We arrive at the same thing, but we still get the same determinant. And so now, I invite you all, right, if you want to try and maybe get this computation a little easier, right, for the determinant of something, what you can do are these, what we call row operations, right? You can do operations on rows so that everything flows a little bit faster, right? Okay, so that's it, right? That's it. And I suppose that is the end of our determinant properties. For our last video, for this case, or for this little topic right here, we will have our adjoint and our inverse, right? To hopefully tackle one of the biggest questions for this thing. All right, we've tackled addition. We've tackled by reference because of scalar multiplication. We have also tackled subtraction. We've tackled multiplication. What about division? Is that possible? We'll find out, right? So thank you. I'll see you next video.